Okay, hello to everyone on the other side of the screen. Junjie Mao. I'm an X-ray astronomer who knows a little bit about atomic physics. In the next 13 minutes or so, I'll talk about the R matrix electron-impact excitation for the carbonate ions. So the upcoming decades will probably be a golden area for the high-resolution X-ray spectroscopy in astronomy. Next generation of spectrometers on board this mission will provide us with a huge number of high-quality X-ray spectra with unprecedented spectral resolution and statistics. We can better quantify all kinds of physical properties of our favorite targets. And needless to say, plasma codes play an important role here in interpreting the observed spectra. Whether you realize or not, all the plasma codes are built on a large and ever-increasing amount of atomic data of all kinds of atomic processes, including excitation, de-excitation, ionization, recombination, etc., etc. And this talk will only limit to the electron-impact excitation. This is the process where we have a free electron happily floating around in an astrophysical environment. And when it meets an ion, sometimes it gives away some energy, it can be a cool electron, and a bonded electron receive this energy and then go up to an upper level and come back down to a lower level again by releasing a photon. And this is a photon actually contribute to the emission lines that we see in the spectrum. And here you can see a plot that I adapted from the Hitomi atomic paper, where we see percentage contribution of various atomic processes in the helium-like ion 25 line that we see in the Hitomi spectra. And we see that the contribution of electron-impact excitation, color-coded in blue, contributes to about 20% to the forbidden line and more than 80% to the allowed transition. Given the importance of this atomic process, now let's take a look at the data available in our favorite plasma codes. Let's first take a look at the data for hydrogen-like ions in the SPECS code. Actually, I see there are some interpolation going on there. To be more specific, for example, we have R matrix data for hydrogen-like carbon and hydrogen-like neon. And then for all the elements in between, including nitrogen and oxygen, we're actually using interpolation along the isoelectron sequence following some scaling relation. And then for carbon-like and neon-like ions, we actually have patchy data, means that we only have data for cosmic abundant elements, and we don't have for cosmic rare elements. And the situation actually gets even worse when we talk about nitrogen to fluorine-like ions, where we only have data for iron and nickel at the moment. Of course, we are talking about high-resolution X-ray spectra at the moment, so we are also very interested in many resolved lines. And now I take a look at the level resolved atomic data in the Chianti database. And I see a pattern there. We actually have more R matrix data for the low-lying levels and more distorted wave data for the high-lying levels. And for those it is new to you, these two terms, I just show you a plot to give you an impression of what this is. Here we are looking at the cross-section of the collision process as a function of energy. And you can see that the distorted wave calculation gives a good description of the background or the continuum you see in the cross-section, while missing out all those narrow resonance features. And this is where the R matrix calculation kicks in. Of course, it comes with a surprise that the R matrix calculation are way much more computational expensive to calculate. So here I'm using the atomic data in SPECS and Chianti simply because I'm more familiar with these two codes, but actually you will not be surprised from the similar patterns in other atomic codes. In short, we all want our plasma code to be accurate and complete, but we are not there yet. So since 2009, the UK APAP network has been producing a systematically electron-impact excitation R matrix data for several isoelectronic sequences. Many of them are available on open ADAs have already been incorporated into the plasma codes. And the first one is the fluorine-like one, and the most recent published one is carbon-like one, and the nitrogen-like one will be soon submitted, and I'm doing the calculation for the oxygen-like one. And for all these three sequences, I included 27 configurations, which lead to about 500 to 700 levels and hundreds of thousands of transitions for each ion in these sequences. Then we provide rates over a wide temperature range, covering 6 orders of magnitude in temperature. And then we also provide data for all the ions up to zinc for each isoelectronic sequence. Just to give you a little bit more detail of the calculation, here we opt for the combination of all the structural code and the ICFT method to do the structure and the scattering calculation respectively. There are, of course, many more other options out there in the market, but this combination allows us to do large-scale armature calculations for many ions in a relatively short time. But this comes with a price that for low-charge ions, we have difficult data, and this is an example of nitrogen-like oxygen 2, the same for carbon-like oxygen 3 as well, where we can see the black one is the present results, where we have less accurate data compared to other armature calculations. So users need to be used with caution, especially for the optical astronomers here. But for most of the ions, we are actually fine. Here, I show an example of nitrogen-like silicon 8, where we are comparing some key diagnostic lines in the solar observations, and the top 3 panels are the strong resonance transitions, and the bottom 2 are 2 forbidden transitions. And as you can see here, most of the resonance lines, the calculations from various papers agree more or less well. While for the forbidden lines, we do see some difference, especially with respect to earlier calculation by Bell et al. This is also the data that is incorporated in Chianti version 9. And I should also point out that there is vertical dashed line. This marks the upper limit temperature range of the data of Bell et al. And what you see at the temperature, high temperature is actually extrapolated. So this is something that sometimes occur in atomic database as well. Now let's take a look at the application of our new atomic data. And here we are looking at the case where we try to determine the density of solar corona. And there are 2 important lines here. The first one is a UV line, and this is actually one of the most strongest transitions in this carbon-like argon-13. And we plot the effective collisional strength as a function of temperature, and you can see that the recent calculation agree more or less well with the previous distorted wave calculation. But for the near infrared line, this where the transition we have to go from the first metastable level to the ground transition, and we see large difference here. And I should note that this line has actually not been observed until recently. We have the new 4-meter solar telescope. And by comparing the line ratio of these 2, we can actually measure the density of the solar corona. But you also see the immediate effect. If we have different atomic data in our codes, we'll probably get different numbers of the density. Density diagnostics with metastable lines are also in principle possible in the X-ray band. And this is also where my interest is. And for high density winds that are running away from black holes, their metastable levels can actually be populated by electron-impact excitation. In this case, we will not only see absorption lines from the ground level as we normally do, but also absorption lines from metastable levels. And the line ratio of the 2 tells us the density of the plasma. Higher the density, the stronger the metastable line, and the weaker the ground transition. So, but recall that I was saying that we actually have many gaps in our database, in atomic data in the specs code. This means that when we are, I should say that we also can get from the spectra that the ionization temperature, ionization parameter, where combining these 2, we can actually infer the distance of the wind to the black hole, and thus its impact to the surrounding media and the host galaxy. But recall, I was saying that we actually have gaps in our atomic database in the specs code, this means that we actually don't have as many ions as we want to cover this two-dimensional parameter space. And this is the limit of the current theoretical calculation. But on the observation side, we are also limited by the current instrument. The current grating spectrometers do not have sufficient large photon collecting area, so we do not have good enough statistics. Also, we do not have good energy resolution to actually resolve the metastable lines, the line profile clearly. So actually, future missions like ARCUS are really essential to advance our knowledge of the physical properties of winds running away from black hole. So coming back to the golden area we are in, and CRISM will be launched in a year or two, Athena in about 10 years, and Reno has been pushing ARCUS from the US side, and we are also pushing the mission called HUBS from China. And if this new mission is new to you, feel free to ask me a question or check one of my backup slides. And essentially what we are here to do is actually using the, yeah, thanks, last slide. Here I'm actually, we are all looking forward to do new exciting science with the powerful specs and new missions, but also we need to take care of what is inside the black box here. This talk is limited to a theoretical calculation of a specific atomic process, limited by my limited knowledge. But of course, thanks to this workshop and thanks to many previous talks and also following talks and posters in this workshop, we can see actually there are more theoretical calculation and lab measurements going on. And clearly, a joint effort is really needed to prepare ourselves for the new mission. And I'll stop here and take questions. Thank you all for listening.
Okay, thank you. Let's see, now you can write questions in the chat or on the Slack, right, the Slack questions, if you have questions. I just wanted to comment that in your highly ionized argon, where you showed a density sensitive diagnostic between the near infrared and the far ultraviolet, or the X-ray, 249 angstroms. That's a very tough one to measure directly.
Yes, yes, actually we won't be able to do simultaneous measurements.
So find things that are close together. That's the powerful one that we can really make use of. Let's see, other questions? Who's out there hiding?
We have one on the chat window from Chris Stone, Andrea.
Okay, the metastable levels can also be populated by UV soft X-ray photons as well as by electron collisions. So how do we model the effect of the photon field? This is from Chris Stone.
Yes, so actually we, in our specs code, we take into this account. So it is not the only way to populate the metastable levels.